If you compare the world's smallest mammal, the Etruscan shrew, to the African bush elephant, their lives seem to operate on different clocks. The tiny shrew only lives for about a year and a half, while the elephant easily reaches 65. Yet, despite these massive differences in time, both animals receive the same biological allowance, around 1 billion total heartbeats. Scientists once struggled to understand how these traits scale across such vast differences in size. In 1962, CIA-backed researchers tested this by giving an elephant named Tusko a dose of LSD. Knowing the safe amount for a cat, they figured since Tusko had 1,000 times the mass, he needed 1,000 times the dose. Tusko collapsed and died within 5 minutes. The researchers had relied on a flawed premise, that a biological response to a chemical scales in a straight, linear line with body mass. Biological reality is more complex. As animals increase in size, the speed at which they process chemicals and the speed at which their hearts beat slows down according to a highly specific, non-linear curve. This raises a question about the pacing of life itself. Nature refuses to scale in a straight line, instead using a hidden geometric rule that traps almost every mammal within that same 1 billion heartbeat limit. The secret lies in metabolic rate, the measure of how fast an organism burns energy to keep its cells functioning, and how much waste heat it radiates into its environment. There is a strict thermodynamic price to being big. Because an animal's volume grows much faster than its skin's surface area, a massive creature burning energy at the same rate per cell as a tiny one would generate more heat than its skin could ever release. Without a change in the math, the elephant would boil alive. In the 1930s, Max Kleiber discovered that nature avoids this crisis by granting larger animals an energy discount. Plotting energy consumption against mass, data points align on a 3/4 slope. An elephant burns far less energy per pound than a mouse. This single fraction also predicts brain size, blood vessel width, and growth speed, all locking into place along this same mathematical line. Biological efficiency scales brilliantly as animals increase in size. But for nearly 70 years, scientists lacked a physical explanation for why this 3/4 law existed in the first place. The explanation arrived when researchers realized every living creature has to solve a 3D logistics problem: how to transport fuel to every single cell using a network of thin, one-dimensional pipes. To reach every cell efficiently, nature uses space-filling fractal networks. These systems of branching blood vessels fold and split in a repeating pattern that minimizes energy loss, allowing a massive amount of delivery surface area to fit within a finite volume. These networks distribute energy slowly in larger volumes, physically stretching lifespan while slowing pulse. Multiplying lifespan by heart rate, mass cancels out completely. Only a single constant remains. For both shrew and elephant, total heartbeats from birth to death land at roughly 1 billion. The 1 billion heartbeat limit is the unavoidable geometric consequence of pumping energy through a physical body. Humans are currently the only mammals on Earth to exist outside this universal mathematical boundary. 3 centuries ago, our lives were much closer to that billion-beat limit. But by establishing germ theory, better sanitation, and modern medicine, we systematically removed the natural hazards that naturally cap a mammal's age, tripling our heartbeat count in just a few generations. This progress hasn't been a straight line. Historical life expectancy records show clear dips where global traumas, like the 1918 influenza pandemic, temporarily forced us back toward our biological baseline. We see the same interruptions during periods of total war. The conflict of the 1940s created a visible drop in the otherwise upward trajectory of the human lifespan. Despite these setbacks, we achieved the lifespan of a much larger mammal by building external networks to share resources and information. We built cities. Cities scale with the same efficiency as biological organisms, but with an added bonus. While shared infrastructure, like roads and gas stations, requires fewer resources per person as a city grows, socio-economic factors like total wages and patent filings grow superlinearly. A city that is twice as large doesn't just have double the innovation, it has roughly 120% more. This urban engine creates a massive surplus of wealth and ideas, providing the scientific breakthroughs needed to push our hearts past their internal limits. By moving from the internal fractal networks of our bodies to the external networks of our cities, we have effectively transitioned into a macro-organism, becoming the first species to move beyond the geometry of a single life.